Do-do-do-do. Direct variation. Chapter 14.6. Wait, 14.6. Direct variation. I don't know about you, but nothing gets me more excited than direct variation. I'm feeling tired just seeing those words. But you know what? It's actually cool. I know I always say that, but it is. And it actually really means a lot later down the road. We'll get to that. What does the graph look like when y and x are proportional? I know some of you still are like, I don't want to learn the words. I don't want to learn the words. What does proportional mean? It means that if you had some y to x, right, some value y, we don't know what it is, and we'll call it y1 and x1, the first x and y value. If it's proportional, that means that y2 over x2, so some other point x2, y2, and you'll learn this as we go along, that these will be equal. As fractions, they'll be equal. Y to x, they'll be equal. So let's take a look at this in the key idea. Direct variation, two quantities, x and y. Remember, we usually do y to x because we're thinking about slope, and slope is change in y over change in x. But anyway, two quantities, x and y, show direct variation when y equals kx. What the? Where k is a number. That's brilliant. K is a number, okay? And k is not equal to 0. Well, that kind of makes sense. If k was 0, it'd be y equals 0. And it would get rid of x altogether. So how could x and y be proportional? That's where we're headed if k is 0. I don't know what this k business is. I actually do, but I'm going to show you. The number k is called the constant of proportionality. This is a little definition. So apparently, we have direct variation if y equals kx. And if y equals kx, then y and x are proportional. Okay, well, whatever. So if we have y equals kx, that means y to x shows direct variation, which means they're proportional. It's a line. Okay, this is already helping us answer this essential question with a slope of k. That's interesting. So slope and k are the same thing. And it also, this line passes through the origin. That's 0, 0. So there it is. It's a line. It passes through the origin. So the two quantities that show direct variation are in a proportional relationship. Okay, let's take a look at what that means. So we need to find some points on this graph. So how about 1, 2? See how that's on there? 1, 2, and then also 2, 4. So those are 2 points that are on our graph. So we have 1, 2, and we have 2, 4. Now, if this is direct variation, if y to x is direct variation, that means that these should be proportional when I write them as y over x. So y is 2 over 1, x is 1. That should be equal now to 4 over 2. Are those two fractions equal? Yes, they are. They're both equal to 2, right? 2 divided by 1 is 2. 4 divided by 2 is 2. So I'm finding their values. They're both 2. They're equal, so they're proportional because they are equal fractions. And this line does seem to show direct variation because the y to x is proportional. The only point that's not true for is 0, 0. So if you had chose 0, 0 as one of your points, you couldn't write that as a fraction y over x, because then you'd have 0 over 0, and we can't have 0 in the denominator because it breaks the space-time continuum. But anyways, any other 2 points would have worked. So let's now go into our first example. I'm sure you're so excited. Look at you. Gosh, calm down. What are you, Mr. Plunkett? Okay, question. It says, how do I know if x and y show a direct variation? Okay, here we go. It says study tip. Other ways to say that x and y show direct variation are y varies directly with x, or you could say x and y are directly proportional. Okay, these are just different ways you'll see it said. So direct variation means the y to x are proportional. That's what's up. Tell whether the table shows direct variation by graphing the points. 2 dots. I'll get rid of one of those. But look, it looks like a little guy with a little blue mouth. Anyway, do these show direct variation? Well, we just graphed it. We plotted the points. I did it for you, and then we drew a line. Is this direct variation? Well, it's a line. Check. Does it pass through the origin? No. This is not direct variation. These points, y to x, will not be proportional. Just to prove that, let's do y to x. That'd be negative 2 over 1. Is that equal to, and we can pick any one of these other points. I can pick the 2, 0, because this would be written as y over x. That's 0 over 2. Are these equal? No. Negative 2 divided by 1 is negative 2. 0 divided by 2 is 0. Those are not equal. These are not proportional. If the relationship between x and y varies directly, all of the ratios y to x will be equivalent. Remember that word? It means they'll all be equal. These are not equal and therefore are not proportional. If the relationship between x and y varies directly, its graph will pass through the origin, and it'll also be what? A line. This is a line, but it doesn't pass through the origin. It has to satisfy both being a line and passing through the origin to be direct variation. Man, we're doing good on this. Or I should say I am, with my cat kind of looking at me strangely. Gizmo, you gotta stop just wanting food from me all the time. All right, can we do this in one video? I think we can. This is gonna be tough. Do x and y show a direct variation, and explain. Tell whether the two variable equation shows a direct variation. All right, now, instead of a graph, we're looking at the equations. And if you remember this, y would be equal to kx. We have to be able to write our equation in this form. Otherwise, it is not direct variation. Well, notice what's by itself over here. What's by itself? Y's by itself. Y's by itself. Is y by itself on the left side of this equation? No, y plus 1. But if you remember the properties of equality, I could subtract 1 from both sides of this equation. Plus 1 minus 1 is just y. Sweet, that's what we wanted. Equals, because we subtracted 1 from both sides. 2x minus 1, these are not like terms. They don't have the same variable, so we have to keep them separated. So that's 2x minus 1. All right, cool. So let's see if this equation looks like y equals kx. Y equals 2x minus 1. Okay, the y is the same. The equals is the same. The 2 must be k, which is the slope. And then the x is the x. That's fine. And then minus 1. Wait, there's no minus anything on direct variation. This is not direct variation. Because of that minus 1. Whoa. Okay, next one. So how can we tell if this is direct variation? We need to get y by itself and then see if it's in this form. So what if I, how do I get rid of the 1/2 so that I just have y? I could divide both sides by 1/2. Or, I hope you remember this, you can multiply both sides by 2 over 1. And since this one's not a fraction, we can just multiply that by 2. Okay? There's over 1 over 1. The 2's cross cancel, and I'm left with just y. That's what we want. Equals, what's a y? Remember, kids, if you make it thick enough, everything's right. Okay, equals x times 2 is 2x. We always write the coefficient in front of the variable. Okay, so this one's y equals 2x. Is this in y equals kx form? Let's check. Y is y, equals is equals, k is 2, x is x, and there's nothing else. This is direct variation. I don't know why I'm capitalizing this time, but okay, direct variation. Oh, does he have enough space? Can he do it? Woo! With the period too. Jeez, Mr. Plunkett. You didn't even need a period either. All right, anyway. Okay, this one. Wait, y's in the denominator. Why? Why? How can I get y out of the denominator? And this is a really good problem to practice this on. If you have a variable that you want to get alone in the denominator, you know what you can do? You may not know this. This is a secret passed down by generation to generation. You can multiply both sides by y over 1. Or on this side, just y, because, of course, there's no fraction here. The y's cross cancel on this side, so you get rid of the y on this side, but then the y on this side, this becomes 2xy. So now the y's in the numerator. Oh, but y is not by itself. Well, I know that everybody's like, you know, oh my gosh, we're stuck. Can you divide both sides by 2x? Yeah, of course you can. 2's cross cancel, x's cross cancel, and I get 3 over 2x equals y, or I can write that with the y on the left side, y equals 3 over 2x. Now, let's see over here if this is in y equals kx form. I hope you're already seeing that it's not. In y equals kx form, x is in the numerator, right? Here, x is in the denominator. It has a roof over its head. And so we are going to say that this is not direct variation. And then, hold on, my computer is going very, very slowly. I don't know if you can see it, but I have the little wheel of death. Okay, so this is not direct variation. And since I'm running out of space, I'm just going to put NDV, not direct variation. And let me, well, I guess we have enough space. Okay, this one, whoa, what a mess. Hopefully you know this. You can combine like terms before we start. 4x plus 2x is 6x is equal to y minus x. I almost have x or y by itself. What do I need to get rid of? Minus x. Can I add x to both sides? Sure, you can do that. What's 6x plus 1x? 7x equals y. I'm going to flip that turn around. Is this in y equals kx form? Y equals 7x. Yep, y is y, equals is equals, k is 7, which is the slope, and x is x. So this is direct variation. I'll put a little exclamation point because we're so excited. To determine if the relationship between x and y varies directly, you can write the equation in the form y equals kx. To check if equation shows direct variation, solve for, which one were we solving for? We were getting which variable by itself? We were getting y by itself. Using the what of equality? The properties of equality. Whoa. Careful, if y is in the denominator, you must multiply both sides of the equation by y to get it into the numerator on the other side of the equation. You've all been such a lovely audience. This may be one video. I don't know. I'm not sure. We'll have to see how this ends up going. But you've been amazing. Keep up the good work. I'll talk to you later. Bye.